I'm Dr. Joshua Reichard, Associate Faculty in the Forbes School of Business and Technology at the University of Arizona Global Campus, and this is an overview of Module 3 for CPT304, Operating Systems Theory and Design. Regarding CPU scheduling, our goal is to achieve maximum CPU utilization through multi-programming. We know that the execution of a process consists of CPU bursts and I/O waits. A short-term scheduler selects processes from the ready queue to make scheduling decisions. This selection can occur when a process switches from running to waiting, or ready to terminating. The dispatcher module plays a crucial role in handling control of the CPU to the selected process by switching context, transitioning to user mode, and jumping to the appropriate location in the user program. We also need to consider dispatch latency, which is the time taken by the dispatcher to stop one process and start another running. Moving on to memory management, we understand that a program must be brought into memory to execute it. Main memory and registers are directly accessible by the CPU, whereas the memory unit only receives addresses and read-write requests. Base and limit registers define the logical address space to ensure protection and correct operation. They provide a means for the CPU to check every memory access generated in user mode and verify that it falls within the specified boundaries. This week, you will evaluate 3 memory allocation algorithms that operating systems utilize. The first fit algorithm allocates the first available memory block that is large enough to accommodate a process. The best fit algorithm selects the smallest available memory block that is just large enough to fit a process. And the worst fit algorithm allocates the largest available memory block to a process, leaving behind larger unused fragments of memory. Address binding is a critical step in program execution. Programs are typically stored on disk and must be loaded into memory for execution. Address binding can occur at different stages: compile time, load time, or execution time. If the memory location is known beforehand, absolute code can be generated during compile time. On the other hand, load time binding generates relocatable code when the memory location is not known at compile time. Execution time binding allows for delayed binding until runtime, especially when a process can be moved between different memory segments. Hardware support, such as base and limit registers, is required for effective address mapping. Now, let's briefly discuss the multi-step processing involved in executing a user program. It starts with the preprocessor, which handles macros and file inclusion. Next, the compiler translates source code into assembly language. The assembler then converts assembly code into machine language instructions, ones and zeros. And finally, the loader brings the program into memory, ready for execution. Each step plays a crucial role in preparing the program for successful execution within the operating system. I mentioned in my welcome announcement and personal introductions that one of my hobbies is repairing and restoring vintage computer systems. So I thought I would share an example from an otherwise ancient operating system, Windows 3.1, which came out in the early 90s. In this example, we see the window for the settings for virtual memory in Windows 3.1. In Windows 3.1, virtual memory was implemented through a swap file, which serves as a temporary storage space on the hard disk. When the physical memory, that's RAM, was insufficient to hold all the running programs, part of the inactive programs and data were moved to the swap file. This allowed Windows 3.1 to effectively manage memory resources by swapping data between RAM, physical memory, and the swap file, virtual memory, as needed, providing an expanded virtual memory space for running applications and even allowing the illusion of multitasking in a 16-bit operating system. Now, what was interesting is Windows 3.1 was not a true multi-process operating system. In fact, the most that can be said is that it was a task swapping operating system, and it achieved this illusion of multiprocessing or multitasking using virtual memory and moving what is in physical memory to the swap file in and out to switch between active applications. Virtual memory is a technique that allows the execution of partially loaded programs. Not all parts of a program need to reside in memory simultaneously. By separating logical and physical memory, virtual memory enables more programs to run concurrently, increases CPU utilization and throughput, and reduces I/O operations required to load or swap processes. It achieves this by mapping logical addresses to physical addresses using the Memory Management Unit, or MMU. In certain scenarios, virtual memory size may exceed the physical memory available. The MMU maps logical addresses to physical memory using techniques like demand paging or segmentation. This flexibility allows for the efficient execution of programs even when physical memory resources are limited. We've covered important CPU scheduling and memory management topics this week. Understanding these concepts is crucial for designing efficient operating systems. We'll explore more about operating systems theory and design in the upcoming weeks. Thanks for your attention and your active participation in week 3.